Think of training a machine learning model like exploring a vast physical landscape. In this three-dimensional space, your elevation represents the model's error rate. The higher you are, the more mistakes the model is making. In a perfect world, this terrain looks like a completely round, convex bowl. If you drop a marble into it, gravity pulls it straight down to the absolute center, reaching the bottom where the error is practically zero. But real-world data frequently creates a long, narrow valley, resembling a deep taco shell. Taking steps that are too large causes the model to lose control. It ends up ricocheting off the steep walls, oscillating wildly without ever reaching the bottom. Surviving this steep terrain requires a drastically reduced learning rate. Taking tiny, highly controlled steps is the only reliable way to keep the model moving safely down the slope. To know exactly how big of a step is safe, data scientists mathematically map the precise curvature of this valley. They do this by extracting two critical measurements from the data: eigenvalues and eigenvectors. Eigenvalues measure the exact stretch factor of the terrain, telling you precisely how steep the walls are. Eigenvectors act as a compass, pointing in the specific directions of those stretches. For any matrix defining a surface, data scientists can extract these exact directional metrics instantly using 2 lines of Python code. The computer returns the results immediately. The eigenvalues come out as clean, simple integers, -3 and 2. But the eigenvectors output as a grid of messy, unintuitive decimals. Looking at those long decimals, it is unclear how the algorithm actually arrived at those specific coordinates, or where those values physically originate. Truly understanding an automated machine learning tool requires reverse engineering the hidden mathematical logic to see where those decimals come from. To do this manually, we start by finding the eigenvalues using a characteristic equation. Through algebraic expansion, we subtract a variable called lambda from the matrix and factor it into a quadratic equation. Solving that equation gives us our exact multipliers, -3 and 2. That -3 is an exact measurement of magnitude. It indicates that along a very specific axis, the data terrain is being stretched by a factor of 3 and flipped in the opposite direction. We then plug that -3 back into our modified matrix to solve for the x and y coordinates, allowing us to find which way that stretch points. This process bridges the gap between an isolated numerical multiplier and a physical geometric direction in space. Plugging in -3 simplifies the matrix to a basic linear equation, -2x plus 2y equals 0, which reduces to x equals y. Textbooks often skip a step here, simply assuming x equals 1. This forces y to equal 1, giving you a final vector of 1, 1, a choice that feels completely arbitrary. The equation x equals y describes an infinite continuous line. Any point on this path, 1, 1, 5, 5, or -100, satisfies the requirement. Multiplying an eigenvector by any numerical value scales its length, but its angle remains constant. It will always point along that exact same track. We can see this in our second eigenvalue, the +2, where the coordinates are not symmetrical. As shown here, setting the determinant to 0 creates an equation where y equals 3.5x. Whether we input 1, 2, or -10 for x, the y-coordinate maintains that exact 3.5 ratio. Eigenvectors represent a strictly locked directional ratio, a rigid path of data transformation that remains independent of scale. While the manual vectors are simple whole numbers, the Python script generates messy decimals because computers utilize a standard called normalization. Computer libraries shrink the infinite line down so the vector has a total physical length of exactly 1 unit. For our second eigenvalue, this unit eigenvector results in the coordinates -0.27 and -0.96. Standardizing these vector lengths allows machines to universally compare different directions in the data, regardless of the original scale of the numbers. These matrices map the actual geometry of the model's error landscape. To analyze this surface, we look at the Hessian matrix, which describes the curvature of the landscape at any given point. By taking the ratio between its largest and smallest eigenvalues, we calculate the condition number. A massive condition number serves as an immediate diagnostic warning that the terrain is dangerously steep in one direction and very flat in another. Engineers use this metric to decide when to lower the learning rate, preventing the model from oscillating out of control as it descends the narrow valley. Mapping the eigenvalues of the Hessian provides the precise navigational instruments needed to traverse hazardous terrain and reach the right answers.